Back in 1987, flash memory cost about $80,000 per gigabyte. 20 years later, in 2007, prices had fallen to just $10 per gigabyte, and by 2014, just 27 cents. And then, as of this writing, spot prices were quoting just about 2 cents per gigabyte, and that is some insane scaling. Moore's law might have faltered in the logic world, but it is still alive and well in flash memory, particularly the variant known as NAND. In fact, one can argue that flash memory, first NOR and then NAND, has been one of the most successful semiconductor products ever made. In this video, the 60-year evolution of flash memory. The heart of flash memory is the floating gate transistor. Like the famous DRAM cell, the floating gate transistor stores a charge. Unlike the DRAM, however, the charge is not stored inside a capacitor, but inside the transistor itself. Imagine a planar metal oxide semiconductor field effect transistor with a source, drain, and a gate controlling the flow between the two. Between the gate and the channel is a thin layer of oxide, the gate oxide. The transistor has a fixed threshold voltage. When a voltage higher than that threshold is applied to the gate, a current can flow through the channel. Yada yada, you probably know all this. The floating gate transistor switches it up by having two vertically stacked polysilicon gates, like the meat patties in an In-N-Out double burger. On top is the control gate, and on bottom is the floating gate. Both are surrounded by an insulating dielectric like silicon dioxide. The control gate is connected to a word line that gives it the voltage for switching. The floating gate, on the other hand, is not connected to anything. It is entirely on its own. It is floating. Ergo the name, floating gate. Electrons can be sent into the floating gate, crossing the insulating oxides. This is called programming. And the gate is so well insulated, once it stores those electrons, it can store them for a very long time, 10 years or more. So how does this map to a bit? For the simple example, when the floating gate is empty, then the transistor basically works the same as it always does. When a voltage is applied to the control gate, a current flows. But when the floating gate has electrons, it raises the whole transistor's threshold voltage. It no longer responds to the same voltage being applied to the control gate, so no current flows through. We can map either state to a data bit. Floating gates were first presented in 1967 by two Bell Labs researchers, Da-Wan Kang, a Korean-American, and Simon Shi, a Taiwanese-American. That first paper noted how the transistor can store data for up to an hour, and mused that it can be used for memories that retain their data even when the power turns off, called non-volatile memories. The first popular non-volatile memory based on the floating gate transistor structure was the electrically programmable read-only memory, or EPROM. Inventor Dov Froman had troubleshooted a process issue with one of Intel's first chips, the Intel 1101. A theory he investigated was the transistor's gate losing its connection and quote-unquote floating. Later, this thought inspired him to invent the EPROM. Froman said in an oral history for the Computer History Museum that he was not aware of Kang and Shi's work during its invention. That paper only came up later when they tried to patent it. The concepts are quite similar, however. The EPROM's reprogrammability and ability to remember data when the power turned off helped corporate customers develop new products faster, making them Intel's first real cash cow prior to their monstrous success with x86 CPUs. One of the challenges of making a workable memory out of the floating gate transistor is how to get the electrons back out of the floating gate, a process formerly called erasing. Erasing the data from the EPROM required you to shine UV light directly onto the chip for 15 to 20 minutes through a quartz window. Cool at first, but over time it got a bit old. Also, the erasure was rather indiscriminate. The chip's whole content got erased, and producing a package with a quartz window costs more than an ordinary plastic package. So ideally, you want a way to electrically erase a memory chip. In 1976, a researcher at Hughes Electronics named Eli Harari invented the electrically erasable programmable ROM, or EEPROM, or the E-squared PROM, or E-squareds. That's a lot of words. E-squareds made it possible to delete data faster and more selectively, but their structure required having two separate transistors, a memory transistor, which was the storage node, and a select transistor to isolate the memory transistor. Add in the fact that the electrons tunneled out of a special separate tunnel oxide area, and you end up with cells that were rather large, which made the chips costly. Invented in the late 1970s, E-squareds never really got popular, because flash came soon right afterwards. In 1980, a researcher at Toshiba named Fujio Masuoka started a project to simplify an E-squared's two-transistor structure. In a 2006 interview with Businessweek, he said that he wanted to create a chip that could, quote, one day replace all other memory technologies on the market, end quote. A chip that can replace DRAM due to it being cheaper, and a chip that can also replace the floppy and hard disk drive markets, then worth over $90 billion worldwide. Surprisingly, Masuoka, then a sub-leader in one of Toshiba's DRAM factories, conducted his project without the knowledge of his superiors. He worked on it in his spare time and occasionally borrowed the help of his work colleagues. Their new memory cell adds a third piece of polysilicon called the erase gate adjacent to the floating gate with a layer of oxide between them. When erasing data, a negative voltage is applied to the erase gate and a strong positive voltage to the substrate. This creates a strong electric field that causes the electrons in the floating gate to quantum tunnel out into the silicon. This is called Fowler-Nordheim tunneling, though I keep calling it flower. So the erase gate and oxide are like a dedicated exit drain for the electrons, letting us string them together like DRAM does and erase them all at once. This reminded someone of the flash of a camera, ergo the name. Toshiba never commercialized this new flash EEPROM design, but Masuoka did present a paper about it at the 1984 IEDM conference. Intel was there and asked for a sample, which kicked off Toshiba's formal efforts to make a prototype. The media also picked up on the presentation, and as might be expected at a time when economic anxieties about Japan were near a peak, they hyped up its prospects. Though, to be fair, the hype turned out to be right just a few decades early. At the time, there was a team at Intel trying to modify the older EPROM to have the EEPROM's electrical erase capabilities. By thinning its gate oxide, they created what they called Erasable Programmable Read-Only Memory Tunnel Oxide Flash, or ETOX. The more widely adopted industry parlance was NOR flash, and it's a far superior name. And NOR became the dominant flash memory architecture of the 1990s. Intel released ETOX in 1988, marketing it to portable PC and digital camera vendors. These memory chips were expensive and had low capacity, so were mostly kept to specialty devices like the NEC Ultralight or the Pocket Palm-Top computer. But it found a stride when computer makers adopted it to replace the EPROMs that they once used for storing a PC BIOS's code, making the BIOS user upgradable. This was the first major use case for this new memory, and Intel quickly gobbled up 80 to 90% of the market in the late 1980s and early 1990s. In 1986, the U.S. International Trade Commission sued Toshiba for violating DRAM patents held by Texas Instruments. Masuoka was sent to Washington, D.C. as a consulting engineer, and on the days when court wasn't in session, he had plenty of free time and started thinking, as we all do, about the future of semiconductors. NOR's key issue was cost. NOR cell arrays, being similar to DRAMs, are large. This means fewer dies per wafer and lower yields, which drives up cost. If flash memory is to ever compete with magnetic bit hard disk drives, then the arrays need to get smaller. Thinking about this, Masuoka quickly wrote up several patents. One of those would become NAND flash. The key difference between NOR and NAND is size, and that is tied to how memory cells are tied together. Here is a metaphor. Imagine NOR as like a spacious gallery of books. I myself like to imagine the Pantheon. Each book inside our Pantheon gallery sits on its own individual table, and these tables are arranged in a grid arrangement with plenty of space in between, with a simple address that makes it easy to find. This makes it convenient and super fast to get any book. You just walk to it. But it also limits how many books that the gallery can store. NAND is more like an Amazon warehouse. The books are packed tightly together in long rows of shelves. When you want to get a book, you have to wait for it to get pulled out of a shelf and travel down the row to you. The advantage is that you can cram together a lot more books as compared to the spacious gallery. The disadvantage is that you can't just walk down to get your book. There are procedures and compromises. Now let us bring this back to NOR and NAND. In NOR, each cell's control gate is connected to a word line, and each cell's drain is connected to a bit line. This gives us direct access to and from the cell, but also means needing to physically wire them with metal contacts, which are large and take up space. With NAND, we have 16 to 64 memory cells connected together. Each of the cell's control gates are connected to word lines, like as with NOR, though that word line is shared amongst all the cells at that position in the array. The bigger difference against NOR is that most of the cell's drains are not connected to a bit line, but rather to the source of its neighbor cell, creating a string. The only bit line is at the end of that string. There are just 2 contacts in the whole array at each end, which saves a lot of space. But it also means reading data is serial. You can't access single books, but whole rows at a time. So when you need to erase something, you have to erase the whole block. This leads to overall slower read and write times, but most see this as an acceptable trade-off for the smaller size. Upon returning to Japan, Masuoka convinced the head of Toshiba's Consumer Electronics Laboratory to sponsor a project to develop this new type of flash memory, pitching them on using it as a storage medium for digital cameras. Over the next 3 years, the team struggled to make it happen. Meanwhile, the late 1980s was a breakout period for the flash memory market. In 1988, the E-squared inventor Eli Harari, convinced that flash-based mass storage was just around the corner, co-founded a startup called SunDisk, later renamed to SanDisk because Sun Microsystem got all snooty about the name. I shall stick with the latter. At this time, flash chips were just raw, unreliable storage. Unreliable because writing and rewriting data to the floating gate transistor involves compelling electrons to pass through a thin layer of oxide. Done too many times, that oxide layer wears down and eventually fails, leading to bit errors. This, like Thanos, is inevitable, but also a pain in the butt to manage. Eli Harari and SanDisk realized that their only way to fix Flash's inherent problems was to take a system-level, holistic approach. They combined the flash memory dies with an off-the-shelf embedded logic IC called a controller. That controller was programmed with error correction software to detect and handle errors, as well as procedures to lengthen the drive's overall working life, like spreading out wear across the multiple flash dies. In the end, all the PC sees is just another disk drive, a solid-state drive, so to say. All the hairy things gracefully swept under the rug. In 1991, SanDisk caught its big break. IBM was working on a new pen-based tablet PC that they were calling the ThinkPad. The ThinkPad used a traditional 20 megabyte hard disk drive, but it kept breaking whenever dropped. They wanted a solid-state replacement, and SanDisk won the bid. Joining the IBM ecosystem rapidly grew adoption, and soon other vendors brought their own flash-based mass storage products to the market, like flash memory cards, though SanDisk remained the leader with 41% share in 1994. In 1990, after 3 difficult years, the research team at Toshiba put their finishing touches on the NAND product and authorized the start of mass production. The first 4 megabit NAND flash chips hit the market in 1992 as part of a Toshiba digital camera product. Unfortunately, that first camera cost about $20,000 or $44,000 in 2024 dollars, which impeded adoption. But Toshiba pushed on. In 1993, they brought out a 16 megabit NAND flash. Shortly thereafter, Samsung reached out about a partnership. Toshiba, looking to make their new flash product an industry standard, sent 30 engineers to Korea to teach Samsung the 16 megabit NAND product and collaborate on next-generation 64 megabit chips. In a classic case of student surpasses teacher, Samsung went on to become the world's leading NAND flash producer, dominating all the major semiconductor memory categories. And as for Masuoka, he left Toshiba in 1994 feeling rather unappreciated. 10 years later, he sued them for $9 million, a fair share, he says, considering the billions Toshiba made from his work. An unusual step, but a right one, considering. They later reached a settlement. NOR dominated the 1990s, but the following decade, NAND eventually caught up. Since commercialization, both NOR and NAND grew capacity at a rapid, consistent rate. With a few exceptions, fabs largely did this by physically shrinking the transistors, drafting on new technologies like DUV lithography. But new issues began to emerge, particularly for NOR cells. It is time to discuss one of the differences between NOR and NAND cells. As I mentioned, NOR cells are programmed by generating a powerful enough electric field in the transistor silicon channel to compel electrons in the drain to essentially leap over the hedge into the floating gate. This is called hot electron injection, and it is tied to the 3.2 electron volt energy barrier between silicon and silicon dioxide. The field must be stronger than 3.2 or the electrons don't cross. The issue is that such a field requires a strong voltage across the transistor channel, but as NOR cells shrink, their oxides get thinner and more vulnerable to interference from their neighbors as well as general wear and tear. Moreover, if the source and drain get too close together, the voltage compels leakage from the source to the drain. This is the famous short channel effect that so famously bedeviled logic chip makers and necessitated FinFETs. For NOR, the things that can be done to ameliorate this, like thinning the oxide, have knock-on trade-offs that eventually lead to a shorter-lasting memory cell, a tricky conundrum. For NAND, it's different. Their cells being so densely packed together made hot electron injection impractical from the get-go. So Toshiba used the Fowler-Nordheim quantum tunneling method normally used for erasing the cell, and that turned out to be more scalable over the years. The NAND industry also introduced a series of clever and critical innovations to grow storage capacity. One of SanDisk's early innovations, filed all the way back in 1988, involved having a NAND cell store 2 bits rather than just 1, the multi-level cell. This is done with a twist. In an ordinary floating gate transistor, called a single-level cell, the cell only has to map 2 distinct states, and that's because a bit has just 2 combinations, 1 or 0. To have that cell store 2 bits, we need the cell to somehow show 4 unique combinations, 00, 01, 10, and 11. This is done by grouping the charge level into 4 threshold voltage groupings. What does that mean? Imagine a bucket of sand. We draw a threshold in the bucket. With the single-level cell, there's just 1 line. If the sand breaches the line, then 1, no breach, just 0. But with the multi-level cell, we draw more lines in the bucket and start measuring whether the bucket gets to be half full, quarter full, or 3/4 full. Creating more of these voltage steps adds capacity to each cell, but at a cost. Imagine the bucket being divided so many times that it starts getting difficult to measure where the sand level is at. It was hard to do this consistently, requiring a great deal of precision in both writing and reading. One tactic has been to give the chip more time to quote-unquote settle, reducing on noise. So these multi-level cells pull data out of their system more slowly than their earlier cohorts. Toshiba and SanDisk introduced the first 2-bit multi-level cells in 2001 at the 160 nanometer node, literally doubling storage capacity without the need for any new equipment. By 2006, these cells had become the industry mainstream. Over the next 15 plus years, vendors have introduced 3-bit triple layer and even 4-bit quad layer. This scaled the capacity of planar NAND flash by a factor of nearly 2 every 2 years throughout that time period, reaching 128 GB in 2015. Cheap flash memory prices have enabled new generations of popular consumer products. The first products to benefit were the digital cameras. The first digital camera, Fuji's DS-1P, saved images to a memory card made with SRAM, which is a type of RAM, and so does not save data after the power goes out. Flash memory quickly replaced SRAM. Then, in 1995, Casio released the first commercially successful digital camera, featuring a small 1.8-inch color LCD screen and a flash memory card to save pictures to. It kicked off the digital camera boom. Also in 1995, a company called M Systems, co-founded by Dov Moran, introduced the disk-on-chip, generally acknowledged as the first flash drive. It did okay, but I would say the flash drive really blew up only a few years later in late 2000 when they added the USB interface. The small 8MB USB flash drive, called Disk-on-Key, was an immediate hit and revenues tripled in a single year. There are other claimants to be the inventor of the USB flash drive. I make no comment on them. But regardless, the product's introduction sent industry flash memory sales surging from $4.6 billion to $10 billion. After selling M Systems, Moran became a VC and turned around a failing semiconductor maker called Tower Semiconductor, which I think is an interesting story. Then, in 2005, NAND flash got its real breakthrough moment when Apple produced 2 new versions of their once popular iPod products using NAND flash memory, the iPod Shuffle and the iPod Nano. This triggered a wave of MP3 players using NAND flash memory, though Apple famously prepaid $1.25 billion to NAND flash memory suppliers like Samsung and Hynix to corner some 40% of supply, even putting a few competitors out of business. Apple went on to put flash memory into almost all of their devices like the MacBook Air, iPhone, and iPad. Their products' size, durability, and portability would not be possible without NAND's insane scaling. All the way back in 2000, NOR accounted for over 90% of the flash market, but NAND rapidly started to catch up both technically and business-wise, and by around 2004-2005, it surpassed its elder brother as the dominant architecture in the flash memory market. NOR is still used today, particularly for storing critical code that is not often modified, like BIOS, but when it came to mass storage and taking on hard disk drives, NAND pushed on alone. Intel, a NOR flash pioneer, had once won the market, but slowly lost share to the big Asian semiconductor makers. In 2007, they spun off their money-losing NOR flash division as a company called Mnemonics. That new company was then quickly acquired by Micron 3 years later. Finally, at the 15nm node, planar NAND hit its scalar limits, with the control gates and floating gates getting so close together that they interfere with one another electrically. So NAND went vertical. In 2001, a team in Japan published a groundbreaking paper demonstrating 2 NAND cells vertically stacked on each other. Another idea in 2006 from Samsung Electronics' R&D team fabricated 2 vertically stacked NAND memory cells and connected them with a through silicon via connection. Nice, but since you had to literally fabricate cells on top of one another, neither method seemed very scalable. Memory makers eventually moved to stacking alternating layers of semiconductor material on top of one another like a lasagna. These will be the word lines. Then you punch circular holes through those layers and deposit dielectric and metal inside the holes. Your nodes are where the layers and holes intersect, like doors in an elevator shaft. In 2013, Samsung announced that it started to produce a 24-layer vertically stacked NAND for 128 gigabit memory, a breakthrough moment. They have maintained a yearly cadence ever since, and today their VNAND product is now in its 10th generation with over 400 layers. One can argue that flash memory, and NAND in particular, is one of the most successful semiconductor products to have ever been invented. Over the past 40 years of NOR and NAND flash memory history, the scaling has been remarkably consistent thanks to new technologies and clever architectures to store and erase bits. Moreover, flash memory is ubiquitous thanks to all the products that it enables, from digital cameras to USB flash drives to iPods to iPhones to Ultrabook laptops to SSDs, for AI factories. And with the race heating up between Samsung and Hynix in Korea, Micron in the US, YMTC in China, and Kioxia in Japan, the future ahead seems promising. Let's keep stacking. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.